this lecture I am going to focus on simple harmonic motion, which I had motivated in the previous lecture. And what I had said is that if I take a particle moving around in a circle and take its x component x t, the motion is uniform, then x t is given as r cosine of omega t, which in general I am going to now write as x t equals some constant a cosine of omega t. The corresponding velocity v t is minus omega a sine of omega t, and the corresponding acceleration is minus omega square a cosine of omega t, which is nothing but minus omega square times x itself. So, what it means is, as you know, acceleration a t is nothing but the derivative of velocity with respect to time, which is d 2, the second derivative of x with respect to time, and this for simple harmonic motion is given as minus omega square x. So, this is going to be our equation for simple harmonic motion. That means, whenever the displacement is of the form this minus some constant c, where c is positive, times x, c is positive because this is coming from omega square. So, it has to be a positive number. The motion is going to be simple harmonic. And the solution of this equation is going to be of the form, because remember c is equivalent to omega square. So, motion is going to be x t is equal to some constant a cosine of square root of c t and some other constant b sine of square root of c t. Okay. This is, I will develop it mathematically further, but I am motivating you how this equation where d 2 x by dt square, that is the second derivative of displacement or the acceleration, is negative, is proportional to the displacement itself with a negative sign. I am going to get a motion which is simple harmonic. What it means is, since force is equal to mass times acceleration, that means if force on a particle is proportional to minus the displacement, where minus sign means, let us write that also explicitly, minus sign implies force is in the direction opposite to the displacement, right. So, if force on a particle is minus proportional to minus the displacement, minus sign means force is in the direction opposite to the displacement, it will always imply the motion of particle is going to be simple harmonic motion, and is going to perform a simple harmonic motion. So, we have just looked at this particle moving around in a circle, and through that we found out what x t or y t or the displacement is, took its derivative and then turned the whole argument around. We just went back saying that if the acceleration is proportional to the displacement or the force is proportional to displacement, but in the direction opposite, right, the motion is going to be simple harmonic. That makes perfect sense, because if there is a particle at a certain point, if it moves to the right, suppose this is a displacement, unless the force is in the opposite direction, it will not come back, right, it will not go back and forth. So, the force has to be in this direction, and if the particle is displaced to the left, the force has to be in the right direction. That is a physical way of looking at it. So, for it to perform a simple harmonic motion, right, where it goes back and forth in a very, very periodic way, the force has to be in the direction opposite to the displacement. And I have also shown you how to visualize simple harmonic motion. From now on, I am going to call it SHM, which stands for simple harmonic motion, right. So, how to visualize it? I have already given you the tool to do this. Always think of a particle moving uniformly in a circle, right, with constant angular speed or constant speed, linear speed, and take its component on the x axis or the y axis or a combination of the two. That is the way to visualize it. In fact, later I will again come back to this visualization and teach you something called the phasor diagrams, which are very helpful whenever we are looking out at periodic motion like this. But now, let us become slightly sophisticated mathematically, all right, and develop this further. But before that, I want to solve some problems related to whatever we have learnt. So, I am going to ask you problem number 1. What is the general solution for the following differential equation? Okay, I am giving you an equation which is d2x by dt square is equal to minus 2x. This is exactly the kind of equation we were finding out in simple harmonic motion. This is exactly the kind of equation where the acceleration is opposite to the displacement, and therefore, the general solution is going to be x t, which is equal to a some constant a cosine of square root of 2 times t, and a combination with corresponding sine term, sine of square root of 2t. That is the general solution. You take a second derivative, you are going to get exactly this as I showed you earlier, right. Let us take another example. Let us say d2 y t over dt square is equal to minus 5 y. I am using y just to emphasize these are just symbols. What you need to do fundamentally is look at what is the relationship between the symbol which represents the displacement, a second derivative, and the symbol itself which represents the displacement. So, in this case again you see that the acceleration is opposite to the displacement because that negative sign and proportional to the displacement. Therefore, y t again is going to be some constant cosine of root 5 t plus b sine of root 5 t. That is the general solution. You can check it for yourself, right, that if you take the second derivative, it will satisfy this equation. So, this is just looking at the equation where the second derivative of a quantity with respect to some other quantity is proportional to that quantity itself, right, of which I am taking the second derivative, and there is some constant. Let me also give you a general kind of thing. Suppose I have an equation d2y over dx square, and this is equal to minus, let us say, some constant, right, k y, where k is greater than 0. What is the solution? You see, this equation, if I put it on the side, is exactly like d2 x over dt square is equal to minus, say, kx. It is exactly like that. I am taking the second derivative of a quantity, here I am denoting that by y, with respect to another quantity which I am denoting by x, and the second derivative is proportional to y itself. It is exactly the same structure. All that we have done is replaced x by y and t by x. So, the general solution for this is also going to be y as a function of x is equal to some constant a cosine of root k x plus b sine of root k x. So, what you have to keep in mind is that the mathematical structure of the equation, which is in this case second derivative of a quantity, right, with respect to some other quantity is proportional to that first quantity itself, then mathematical structure tells you that the solution is going to be a linear combination or a combination of cosine and sine terms, right. And where in all these three examples A and B are some unknown. They are unknown. Right now, I do not know them. There is no way from the solution that we can find them unknown, but they are constants. They cannot depend on t, x, y, anything. They are constants. The way to determine constants are if we wish to determine these constants, we need further information, and these are two constants A and B, two constants. So, I need two equations to determine them. So, the further information should be in terms of two further informations, right. So, it could be, say, this information could be number 1, displacement and velocity at t equal to some time, let us say t equal to 0, or it could be displacement at two different times, or any information where I need two informations. So, let us solve a general example. So, suppose I have this equation d2 x over dt square is equal to minus omega square x. I have just written it omega square to keep things simple. So, that x t is given as a cosine of omega t plus b sine of omega t. So, this is it, this is I cannot determine a and b any further. And suppose now I give you that x at time t equal to 0 is x 0 and dx by dt, that is velocity at time t equal to 0 is some v 0. Now, I have given you two specific informations, then I can determine a and b. How do we do that? X at t equal to 0 is going to be, if I substitute a cosine of 0 plus b sine of 0, which is a, and this is given to be x 0. So, I have already determined what a is going to be. Similarly, v t at t equal to 0, which is dx by dt, is nothing but minus omega a sine of omega t plus omega b cosine of omega t at t equal to 0 is going to be nothing but omega b, and this I have been given to be v 0, and therefore, b is v 0 over omega. Now, I have the complete solution, and therefore, I am going to have in general x t is going to be x 0 cosine of omega t plus v 0 over omega sine of omega t. This is where the displacement and velocities have been given at t equal to 0. X 0 is displacement at time t equal to 0 and v 0 is velocity at time t equal to 0. Let us solve an example. Find the solution of equation d2x over dt square equals minus 25x with x t equal to 0 equals 3 meters and v at t equal to 0 equals minus 2 meters second inverse. So, I have been given x 0 and v 0, and immediately I can write that x t is going to be 3 cosine of 5 t. How do I get this 5? Because this 25 is nothing but omega square minus 2 over 5 sine of 5 t, which then comes out to be 3 cosine 5 t minus 0.4 sine 5 t. That is the solution. So, you see, I have a general solution of that second order differential equation with a minus sign in front and the second order derivative being proportional to the displacement itself. I have a complete solution if I specify x and v at t equals some given time, which I am taking to be 0 right now, or the displacement at 2 different times, and so on. Okay. With this preliminary introduction, let us conclude that force proportional to minus the displacement implies acceleration, which is d2x by dt square equals minus some constant c x, and this all this together leads to simple harmonic motion, and by that we mean that the displacement x t is going to be of the kind a cosine of some omega t, where omega would be determined by c, right. Omega is equal to square root of c plus b sine of omega t. How do we get this mathematically? So, let us now develop that. This is going to be slightly on the advanced side, but I think you will enjoy it, because by now you must be, I am just giving you arguments that this is how the solution comes out, but if you are getting that feeling how does it come out, let me just give a mathematical digression, detour. Okay. So, I have been given d2x by dt square is equal to minus c x. I am taking c greater than 0. Okay. So, in this case I can, the equation I have d2x by dt square is equal to minus c x. I will assume solution of the form e raised to lambda, somewhere lambda is some constant t. So, I am assuming x t can be written as e raised to lambda t, and therefore, dx over dt is of the form lambda e raised to lambda t. d2x over dt square is of the form lambda square e raised to lambda t. Substitute this in the equation. So, substitute this in the equation, and then what do you get? Lambda square e raised to lambda t is equal to minus c times e raised to lambda t. These two terms cancel, and I get lambda equals plus or minus I root c, and therefore, the general solution is either of the form e raised to I root c t or e raised to minus I root c t, and the most general solution is going to be a combination of the two. This is going to be some constant a 1 e raised to I root c t plus some other constant b 1 e raised to minus I root c t. Okay, so, x t is of the form a 1 e raised to I root c t plus b 1 e raised to minus I root c t. And you will learn, or if you have not already learned, e raised to I root c t or some constant t is nothing but cosine of root c t plus I sine of root c t. Right. So, therefore, x t, if I combine the two, I can write as some constant a cosine of root c t plus some other constant b sine of root c t, where a you can make out is going to be a 1 plus b 1 and b is nothing but I times a 1 minus b 1. So, I can write the solution. I have given you mathematical way of getting the solution. This also teaches you something interesting. If c is negative, okay, that means the force is proportional to displacement, but no minus sign here. Notice no minus sign here. That means, if you displace a particle to a certain distance, force is in the same direction. If you displace in the negative side, force is in the same direction. You can already see physics wise that the particle is going to run away from that point. Let us see that mathematically. In that case, the differential equation is going to be d 2 x by d t square, which is going to be c x, where c is again positive. This minus sign is gone. And if I again take solution x t to be of the form e raised to lambda t, you will find that lambda square is equal to c, or lambda equals plus or minus square root of c. And therefore, the solution x t is going to be of the form e raised to square root of c t or e raised to minus square root of c t. The general solution x t is going to be some constant a 1 e raised to square root of c t plus b 1 e raised to minus square root of c t. And you can see as t increases, the first term increases exponentially, and therefore, the particle is just going to run away. X is going to be keeping on increasing further and further. So, that minus sign in front is very important, which we understand physics wise, is that if f is proportional to minus displacement, right, and f is proportional to displacement, the motion is quite different. In this case, displacement is this way, force is the other way. Displacement is this way, force is the other way. So, this is x, this is f. In the other case, force displacement is this way, force is further this way. So, it makes the displacement grow faster. If the displacement is the other side, force is also in that side. So, it makes the displacement grow farther, and that is shown by this exponentially increasing term. So, this is the mathematical digression that tells you how the solution arises, and how, if that minus sign is not there, the solution, instead of being oscillatory, it will be exponentially increasing, and there will be no oscillatory motion. So, let us summarize what we have learned so far in this lecture. What is new that we have learnt is that if force is proportional to minus the displacement, the equation of motion is of the form d 2 x by d t square is equal to minus c x, and the general solution of this equation is of the form x t equals some constant a cosine of root c t plus some other constant b sine of root c t. A and b are determined by some conditions, in fact two conditions, given. This could be x and the velocity, the displacement and the velocity at a certain time, or two displacements at a certain time, and so on. If force is proportional to displacement, that means no minus sign in front, d2x by dt square is equal to Cx. I must write C greater than 0, C greater than 0, and the particle tends to move away when displaced. So, this first thing leads to what is called as the simple harmonic motion. Now, the question we ask, if we have set up all this mathematical device, where or in which systems does simple harmonic motion occur? That is one question. And two, what is important about simple harmonic motion that we are paying so much attention to it? So, I will answer the first question and then we will go to the second one. In which systems does simple harmonic motion occur? We have already seen if force on a particle is proportional to the displacement, but in the direction opposite to it, SHM takes place. So, one place where this happens is a spring mass system, because you know in a spring which is say of natural length or unstretched length L0, by Hooke's law if the spring is stretched beyond this L0 by a displacement x, then the force that it applies is proportional to the displacement and spring pulls you back. On the other hand, if the spring is compressed by a distance x, the force again is kx and this is in the positive direction. So, it is always opposite to the displacement, all right. This is Hooke's law, where k is known as spring constant. And its dimensions are newtons per meter. Okay. So, if I displace it by 1 meter, how much force it applies, divide that force divided by the displacement gives you the spring constant. So, spring mass system, if I take a spring mass system, let us say on a horizontal frictionless table and put a mass m here, all right, and let my coordinate system be such that x equals 0 is where the equilibrium point is, where the spring has its natural unstretched length. If I displace this mass by x, then the force on the mass is minus kx, and the equation of motion is mass times the acceleration d2x by dt square is equal to minus kx. This is the equation of motion. So, in a spring mass system where I have a spring and a mass attached to it, the unstretched length is L0 and I measure my displacement from x equal this unstretched length. If I displace it to the right by x, right, it experiences a force to the left which is F equals minus kx, or on the other hand, if I compress the spring by x, it experiences a force to the right. So, this is again going to be minus kx, x is negative. So, F will become positive if I write it as minus kx, and the equation of motion is m d2x by dt square is equal to minus kx, or if I divide by m, I get d2x by dt square is equal to minus k by m x. This is exactly the equation that we have introduced you to in discussing simple harmonic motion. This is of the form d2x by dt square is equal to minus omega square x. So, if I identify omega square as k over m, I have the equation of motion d2x by dt square is equal to minus omega square x. It is also written as d2x by dt square plus omega square x is equal to 0, and we immediately know from this that the solution x t is going to be a cosine of omega t plus some other constant b sine of omega t. So, what I have shown you is in a spring mass system where spring follows the Hooke's law, that is the force is proportional to the displacement, you get simple harmonic motion, right. So, in a spring mass system, if the mass is displaced, is going to perform simple harmonic motion. So, here is a spring and this is the mass, right, x equals 0. The solution is x t is equal to a cosine of omega t plus b sine of omega t, where the angular frequency omega is given by square root of k over m, right, where k is the spring constant and m is the mass of the particle. So, to perform this motion, the particle has to be displaced, some motion has to be started. So, if I pull the mass and leave it, right. So, if I do this, let me just show it to you in the picture. This is my equilibrium position L0. What I will do is I will stretch the spring by some distance x0 from here to here and leave it. So, I pull it up to this point and leave it, so that V0 is 0, all right. Then the motion, as we discussed earlier, is going to be x t equals x0 cosine of omega t plus the second term is 0. Let me show it to you explicitly. So, I have x t equals a cosine of omega t plus b sine of omega t. X at 0 is going to be a, and that is given to be x 0. V at 0 is going to be omega a sine omega t plus, with a minus sign, plus omega b cosine of omega t, and that is given to be 0 at t equal to 0. At t equal to 0, the sine omega term is already 0, cosine omega t term is 1, and this immediately implies b equals 0, and this leads to this solution. That is one possibility. Other possibility is I take this spring mass system and give it a hit, so that when it was at t equal to 0 at x equals 0, it got an initial velocity v 0, say in the positive direction, right. So, then from x t equals a cosine omega t plus b sine omega t, and from this condition that x at t equals 0 is 0 and v at t equals 0 is v 0, I am going to get x t equals v 0 over omega sine of omega t. That is going to be the description of the motion. Both are simple harmonic motion. Let us quickly solve a couple of examples. So, example 1, a mass of 2 kg is attached to a spring of spring constant K equals 500 newtons meter inverse. What will be the frequency of oscillations if the mass is displaced from its equilibrium position and released. So, what is given to you is that K is 500 newtons meter inverse, the mass is given to be 2 kg. So, the angular frequency omega is nothing but square root of k over m, which is square root of 500 over 2, which is square root of 250, and that is going to be 5 square root of 2500, sorry, 5 square root of 10 radians per second, or if the frequency is needed, omega over 2 pi, that is going to be 5 square root of 10 divided by 2 pi, which is 2.5 square root of 10 over pi hertz or per second. That is the frequency. Example 2, a mass of 5 kg is attached to a spring of spring constant 400 newtons per meter. When it is pulled from its equilibrium position by 0.5 meters and released on a frictionless horizontal table, what will be its displacement as a function of time. So, what you are given is a spring mass system on a frictionless horizontal table. The mass is 5 kg and the spring constant K is 400 newtons per meter. So, you are given K equals 400 newtons per meter, mass is 5 kg. So, omega is going to be square root of k over m, which is square root of 400 over 5, square root of 80 radians per second, which is 4 square root of 5 radians per second. General motion x t is going to be some constant a cosine of 4 root 5 t plus b sine of 4 root 5 t. However, what you are given is that it is pulled by a distance of 0.5 meters and released. So, that means v at t equals 0 is 0. So, you just pulled it and released it. What is the subsequent motion? So, a is going to be come out to be 0.5 meters, because on the side I will tell you x at 0 is equal to a plus 0, which is given to be 0.5, and x dot, that is dx by dt, not x dot, let us write v at t equals 0 is equal to minus omega a sine of omega times 0 plus omega b cosine of omega times 0, and this is given to be 0. This term anyway is 0. So, b comes out to be 0, and therefore, x as a function of time is going to be 0.5 cosine of 4 root 5 t. We have been talking about simple harmonic motion, and looking at the equation x double dot equals minus omega square x, we have shown that the solutions are a cosine omega t plus b sine omega t, where a and b constants. What we want to show now is that the solution can also be written in the form x t equals a cosine of omega t plus phi, or equivalently some amplitude a. By the way, this a is not the same as the previous a. So, this should not be confused. Maybe I should just write it a bar cosine of omega t minus phi, or some a bar sine of omega t plus phi or minus phi, it does not matter. So, first thing that you check if you want to show that this satisfies the simple harmonic equation is x dot t is going to be equal to minus, let us take the first function first, a bar omega sine of omega t plus phi, and therefore, x double dot t is minus omega square a bar cosine of omega t plus phi, which is exactly minus omega square x. So, it satisfies the equation. More interesting, however, is to see how this a bar and phi are related to the constants a and b. So, let us look at the solution x t equals a cosine of omega t plus b sine of omega t, and let us write this slightly differently as multiply by a square plus b square, and in the bracket I am going to write a over square root of a square plus b square cosine of omega t plus b over square root of a square plus b square sine of omega t. Now, notice that a over square root of a square plus b square is always less than or equal to 1, and so is b over square root of a square plus b square is always less than 1. Furthermore, b over square root of a square plus b square is equal to square root of 1 minus a over square root of a square plus b square square. That you can check very easily. So, I can write cosine of phi equals a over square root of a square plus b square, and sine of phi equals b over square root of a square plus b square, and therefore, x t is equal to square root of a square plus b square cos of omega t cos of phi plus sine of omega t sine of phi, which is nothing but square root of a square plus b square cosine of omega t minus phi. What I have shown you is that x t can be written as some a bar cosine of omega t minus phi, where a bar is square root of a square plus b square, cosine of phi is a over square root of a square plus b square, or equivalently a over a bar, sine of phi is equal to b over a bar, tangent of phi is equal to b over a. So, we have shown that the solution can be written of the form a bar cosine omega t minus phi. I could have taken cosine of phi equals a over a bar and sine of phi to be minus b over a bar, and then the solution would have been x t equals a bar cosine of omega t plus phi. So, depending on how I choose my sine and cosine and those signs, I can easily see that the solution can be written in the desired form. Phi, by the way, is known as the initial phase of the motion, because it is really related to the displacement and velocity and everything at time d equals 0. Let me show that. So, if I take the solution x t equals a bar cosine of omega t plus phi, then x at 0 is nothing but a bar cosine of phi, and x dot at 0 is nothing but minus omega a bar sine of omega t plus phi at t equal to 0, which is minus omega a bar sine of phi. So, the velocity and displacement at time equal to time t equal to 0 are related to the amplitude a bar and the initial phase phi. So, that is another way of writing the solution for simple harmonic motion. The second problem I am going to take in this involves two springs. Attached to a mass. So, the problem says that if we have two identical springs and attach a mass m to them in the following two configurations. So, in one case I attach spring 1, then spring 2 and mass m. In the other case I attach two springs in parallel and mass m. Find, this is 1, this is 2, then we say find the frequency of oscillation of mass m in the two cases. Keep in mind, whether I keep the spring vertical or horizontal, it does not really matter. So, let us take the first case when one spring and the second spring are attached to this mass. All we want to do is displace this mass by amount x and find out how much is the restoring force on this because of the two springs. The springs are massless. So, let us see what happens when I stretch this. The first spring, let us say, gets stretched by an amount y. This end of the spring has been, this mass has been moved from the initial position by x, and therefore, the stretch in the second spring is x minus y. Okay, so, the spring gets stretched by x minus y. Let us now look at the force on the second spring. The second spring has gotten stretched by x minus y, and the force on this side due to the first spring which has gotten stretched by y is k y, and the force on this, because it has gotten stretched only by x minus y, is k x minus y. Now, since the spring is massless, the net force on it must be 0. If it is not, the spring will require an infinite acceleration, and this implies that k y is equal to k x minus y, or y equals x by 2. So, now we have found that as this two identical springs are stretched, if the entire displacement of the mass is x, then each spring gets stretched by x by 2. So, let us make this again. If this is x, this has gotten stretched by x by 2 and this has gotten stretched by x by 2. So, the force on the mass, which is only due to the second spring, is going to be k x by 2, and therefore, m x double dot, because x after all is the displacement of the mass, is going to be equal to minus k x by 2, or x double dot is equal to minus k over 2 m x, and therefore, omega square in this case is going to be k over 2 m, or omega is going to be square root of k over m 1 over root 2. So, the frequency in this case, if two identical springs are attached in series, is reduced compared to a single spring by a factor of 1 over root 2. The second case is simpler. In the second case, the two springs are attached together. So, if the mass is displaced by x, each spring gets stretched by x and therefore, applies a force k x. So, F net in this case is going to be 2 k x, and therefore, x double dot or m x double dot is going to be minus 2 k x, or x double dot is equal to minus 2 k over m x, and therefore, omega is square root of 2 k over m, or square root of 2 square root k over m. So, omega in this case goes up compared to a single spring by a factor of root 2. So, let me just summarize the physical realization of simple harmonic motion, right, One possibility that we have discussed is a spring. Mass system where the spring follows the Hooke's law. All right, that means force Fx is equal to minus kx. In that case, the frequency omega of oscillation is given by square root of k by m, and the general displacement xt is a cosine of square root of k over m t plus b sine of square root of k over